Hello, everybody. Welcome to this online learning visit of the Interact NWE project WOW during the EU Green Week. I'm Katrien Bijl. I'm the project manager of the WOW project, working for the Regional Water Authority Vallei en Veluwe. And I'm also the host for this learning session. I will start introducing the other presenters for this event. Today we have my colleague Erik van den Berg. He's a policy advisor, also at Water Authority Vallei en Veluwe, and an expert on innovation in sewage treatment. We have Koos Wessels. He is the owner of Surtec, which is an international company in the field of sewage treatment, drinking and processed water, biosolids, and sludge. We have Marc Lacroix, who is a process engineer for the company Pulsed Heat. And Pulsed Heat is a company specialized in valorization of sludge and biomass residual flows. In the WOW project, Pulsed Heat is our partner responsible for the pyrolysis part of the cellulose pilot. And last but not least, we have Jappe de Best, who is a lecturer at Advanced University of Applied Sciences in the sector bio-based resources and energy. We can go to the program. Here you see the program of this morning. We start with a brief introduction of the WOW project by me. Then we go to the central topic, of course, of this learning visit, which is the cellulose pyrolysis pilot. We start with some theoretical background information about the aspects of pyrolysis and getting cellulose out of sewage, followed by a virtual visit. And after information on the pilot itself, we continue with the final topic for this event, which is a decision support tool, which will be explained by Jappe de Best. And this tool is developed by several partners of the WOW project to help sewage treatment plant operators in their circular choices. We have 2 specific moments for asking questions, but if you have any burning questions in between, you can always already ask them in the chat, and we will make some time for those questions and the answers during the blocks we made for answering them. Of course, we also have some meeting rules, but I'm sure that you are always already used to these after 1.5 years of digital events. But just to be sure, please make sure that your microphone is muted when you're not presenting, that your camera is turned off. Any questions you can place in the chat. But during the question blocks, you can also raise your hands with the raise your hand button, of course. So we can see who has a question. And last but not least, this meeting will be recorded and will be uploaded on YouTube, just to make sure that people who were not able to attend this morning can always look back at the events that we have. So far for the introduction. Let's start with the WOW project. WOW stands for Wider Business Opportunities for Raw Materials from Wastewater. And the WOW project is a consortium of 14 partners, actually. Before it was 12 partners, but we just extended our project with 2 extra partners. And those original 12 partners come from 6 Northwest European countries. And we are working on one common goal. And this is convincing people that sewage is a valuable source for raw materials. Next slide, please. So sewage is a valuable source. For instance, we can already produce Calmera out of sewage. And Calmera is produced using Nereda granular sludge. And you can use it for several purposes, for example, as a biostimulant in agriculture. We can also produce humic acids out of sewage. Struvite for fertilizing purposes, cellulose, which is of course a topic for this morning, and PHA bioplastics, for instance, and also, of course, clean water. That's almost the biggest stream from sewage, fatty acids, metals, organic matter, and so on. The interesting question then is, why is less than 1% at this moment of these raw materials from sewage reused, or actually, I must say, upcycled? Our theory is that the potential of this big source of valuable materials is still unknown by the market. It's also a technical challenge to extract raw materials. It's quite complex to build installations. You will hear it soon from my colleagues and from our partners to extract those raw materials in a way that it can be used by the markets. Thirdly, sewage has an image of dirty and unsafe by the people who are not familiar with it. And of course, that makes sense because years and years ago, we created sewage treatment plants to clean our water and to purify it as soon as possible. And what's left of it, the sludge, well, it still has an image that it's not safe for any other purposes than to burn it. And last, the legal framework to commercialize raw materials is quite complex. Yeah, you can click on. But the opportunities are very promising. If you look, for example, at the case of cellulose, you can make bio-oil and biochar from it. This is also the topic of this webinar. If you extract cellulose from sewage, it will reduce more than 2.53 tons of CO2 equivalents in the sewage treatment chain. This is equal as 4.7 million return flights from Amsterdam to Sydney, to make a comparison which sounds a bit more familiar for you. If you look at lipids, you can make biofuel from it, and lipids are extracted, can also be extracted from sewage. And lipids could replace around 0.2 to 27% of the biodiesel demand on European markets, and that depends on where in the sewage treatment plants you extract it. If you extract it from the beginning of the sewage treatment plants, this 27% is the potential. And last, PHA bioplastics have a potential production of 1.03 million tons PHA per year from sewage treatment plants in Europe. That's substantial. So therefore, in the WOW project, our goal is to show that it's technically possible to recover raw materials from sewage. We would also like to create a European framework for the steps that need to be followed from waste to raw material. So actually, that's the end of waste process. And we would like to make the market parties become acquainted with the potential for materials from sewage. And we hope when the WOW project ends that we have created 5 value chains for our bioproducts from sewage, that we have 3 pilots. Well, those are already there. We will tell you more about that soon. That we have a supporting tool to help sewage treatment plant operators in their choices to a circular approach. That's the decision support tool that we've created. And finally, that we also create a European legal roadmap to have one clear framework to show how you come from raw materials to valuable products. In WOW, the whole project is around 3 pilots. One pilot is about biofuel from lipids using the effluent from the primary treatment. We have a pilot consisting of extraction of PHA bioplastic using primary sludge. And we have the cellulose pilot, in which we extract bio-oil, acetic acid, and biochar using cellulose from screening. And so far, we have those 3 pilots almost more or less running. We created an overview of the current value chain and the market potential in Northwest Europe. And we made 5 legal action plans for 5 Northwest European countries to show which challenges we have in the current situation to create a valuable source from raw materials from sewage. If you have any burning questions so far, please include them in the chat. And I will now ask a question to my colleague Erik, because I was not involved in the pilot from the beginning.
Yeah, Katrien, thank you. My name is Erik van den Berg. I'm policy advisor by the Water Authority Vallei and Veluwe. And in 2016, we came in contact with Pulseed and CITEC, and jointly we saw an interesting opportunity for an innovative concept to synthesize and market bio-oil and biochar from cheap material, mainly consisting of cellulose, derived from wastewater. We decided to join together and apply for this WOW project.
Thank you very much, Erik. We now continue with the presentations of Koos and Mark about the cellulose pilot. And before we do that, I would like to point your attention to 2 other events we are organizing next week. One is about the PHA pilot, and this event will take place on Monday, the 7th of June. And the second webinar will be about the Lipids pilot, organized by our Luxembourgish partners. And this event will take place at Thursday, the 10th of June. You can use the same registration link that you received for this pilot to register for those 2 other events. Many thanks, and I will give the floor to Koos.
Yes, thank you, Katrien. Right in on time, back again. Sorry, I might want to, perhaps I will say something that you have already highlighted, but I had to leave shortly the building because of a fire alarm here at the neighbors. But I'm starting my presentation. If you find things double, okay. The purpose for my presentation is to give you a little bit an update on the pilot installation itself. So I'm going to explain you as far as it concerns the implementation and operation of the rotating belt fine screens, and a little bit of the implementation in the treatment works. And after that, I give the word to Marc Lacroix, who is from Pulsed Heat, and he will explain the part of making products out of the screen material that we harvest through pyrolysis. Our pilot is installed at the sewage treatment plant of Ede, and just some numbers of the treatment works of Ede. It is an installation based on the numbers from 2017, when we started this design, of a design capacity of 272,000 people equivalent, having an actual load of 260,000, so it's not fully loaded. Some numbers on COD and BOD, and what is for the rotating belt fine screens important, of course, is the suspended solids, because we remove basically suspended solids and material that are attached to the suspended solids. Capacity of the treatment plant normally under dry weather conditions is 30,000 cubic meters a day, and the average feed is about 38,000 cubic meters per day. We don't treat the full flow of the installation. We made a mass balance over the fine screens at their maximum capacity. So it doesn't mean that the pilot will run always on this, but the capacity of the installation is based on an average flow of about 800 cubic meters per hour, having a total suspended solids of 232 milligrams per liter. This is different than the average number that you find, but we did prior to doing the design, we have made some samples on the influent, what we would receive as an average, and came up to this number. So that's the basics. The efficiency, what we aim for, and there's always a discussion about the efficiency of rotating belt fine screens, but we measured it on black ribbon paper filter is that we expect to have an efficiency on dry solids of about 54%. This would mean that taking into consideration that the discharge of screened material having 6% of dry solids, that we totally will get about 1,800 kilograms of dry solids a day at maximum capacity. Of course, the solids that don't leave the installation with the screened material comes to the filtrate, and that's a little bit less than 50% of the solids going through. If you look at the maximum capacity, it means that we are able to treat somewhat about 35 to 37% of the daily flow. Looking at the downstream installed pyrolysis installation, we expect it to treat a capacity as an average of somewhat between 400 and 600 cubic meters per hour continuously. Treating these 600 cubic meters per hour on a continuous base, also through the first flush, means that we cannot operate it on one rotating belt fine screen, so we installed two. One screen will deal with approximately 350 to 400 cubic meters under normal circumstances, and with the first flush it will be a little bit less. So the situation is that there is a feed pump installed after the core screen, what is 6 millimeters.
I'm
and
sorry
then,
to interrupt you, Koos, but
Yeah.
not anyone can see the slides going through. So a kind question, if you could restart your presentation, that might help.
Restart it completely. Okay, let me see.
Yes, well, only the slides.
Only the slides.
Mhm. Let me see where I'm. Okay, restart it in presentation mode then. Is it visible now?
No, not yet for everyone.
Maybe I restart sharing then. That would help.
Yes, it's good now.
Okay, there we are. I just continue where I was, or do you want me to restart?
You can
maybe-
continue.
Okay. So this is the setup on the capacity, what I explained about 800 cubic meters maximum, 45 or 54% on efficiency on total solids, treating approximately 37% of the daily flow at max. On the average, we will run somewhat between 400 and 600 cubic meters per hour. Installation is set up with two rotating belt fine screens, where we have a feed pump installed after the core screens, what is 6 millimeter core screening, and then there is after flow measurement to measure the capacity split over two rotating belt fine screens that are operating in a master-slave setup. So there's basically one machine up and running, and when we get more solids than it can handle, the second one comes up as well, and they change operation. In the installation, it's running based on the level in the machines. So we set a certain level, and based on this level, the belt speed is controlled. And when we have maximum level and maximum belt speed for some time, the second machine will switch on. During this test, we will test also something new that is not on any rotating belt fine screen installed yet. So there's a novelty in the machine, and that novelty is that we have installed a scraper installation. That we have installed scraper installation that might overcome the necessity. Sorry for this, but we have an alarm here ongoing due to some fire next door. So sorry for that. So we want to overcome the necessity of continuous cleaning with air. Of course, this is a test, but this is part of the research for ourselves. Material is pumped to the pyrolysis installation. A setup for the building that is made. You see some pictures of it. Basically, building is set up in two parts. We have a wet part and we have a dry part. On the right side, you see the wet part where you see installed the two rotating belt fine screens, and water is coming from there to the dewatering machine that is part of the installation of pulsed heat. A quick tour. Of course, we get the online tour, but some pictures of it, then you can recognize it. Here we have the feed pump pumping water after behind the core screen, going into the pressurized side where it's coming up on here in this pipe, where we measure the flow before the split, and it goes over the two rotating belt fine screens. In the middle of these machines, you see a collector where we collect, filtrate the overflow and the bottom flush for discharge. And this is the exit side of the machines where you see the pumps going into the to the dewatering installation. The installation is controlled fully automatic, basically based on settings, and so we can monitor it from a distance, see what is happening. We measure basically all the controls, all the frequencies of all the equipment, meaning that we can make a pretty good mass balance and see the operations. Talking about operation, this is how it will look like when we see the machine having feed water and then the material on the discharge side as well. So this is, in short, my presentation, and I would like to give the floor to Mark. Sorry for the disturbance sometime, but we have some issues here around us, so sorry for that.
Thank you, Koos. I think I've already shared my presentation. Yes, there it is. Hope everyone can see it. I'll also be giving an update in this presentation about the process equipment supplied by Pulse Heat, and I'll discuss the pyrolysis products, and I'll give some regard to the issues or the market opportunities of these products. In my next slide, yes, here it is. I'll to make the explanation of my of the rest of my presentation a bit more easier. I'll give a short introduction of the process. So the thing Koos already discussed is the sewage, that it is partially pumped to the cellulose screens, and cellulose screens are basically a part of the wet part of the installation. So there the cellulose is recovered, and then it will be dewatered. So the dewatering will be shown in the next slide, and after the material is dewatered, it will be dried and made into pellets to be suitable for use in the pyrolysis section. And the pyrolysis section will yield these bio-based products that are very interesting for this project. Okay, here you can see our dewatering machine. So we dewater the cellulose because dewatering is one of the most effective energy by means of energy ways to remove the bulk of water. So as you can see at the bottom left, this is how the cellulose approximately looks like when it is pumped to our press. And the press dewaters it into a cake, and that cake is transported to a buffer. And at the bottom right corner, you can see a picture of the cake in the buffer. And this this buffer is used to physically separate both parts of the installation. So if things happen in the wet part, some process complication, for instance, the thermal part doesn't directly have to get into trouble due to that. And the filtrate coming from this press is returned to the wastewater treatment plant. This is the drying section of the thermal part, and in this section we want to create a suitable pellet that is dry enough to be used in our pyrolysis section. So for that we are using two different dryers. We're using a pollen cotton dryer, and we're using a deep dryer. So the thermal energy necessary for these dryers comes from the pyrolysis of pyrogas co-combustor. And in that combustor, we basically have two separate burners. We have one using propane as a source, and that is our main burner. And when the pyrolysis section, which I'll discuss later, is started, it will produce a flue gas, a syngas, and this syngas is also combusted in that co-combustor. That's also why it's quite large, because due to environmental regulations, you need a certain temperature there of at least 850 degrees. And you also need a certain residence time of 2 seconds. And this gas stream at 850 degrees is going to our fallen coating dryer. In this dryer, also the dewatered cake from the other section is transported using two screws, and it comes into direct contact with the high temperature flue gas. And there, the first section of the dryer, there's a flash, and due to that flash, the bulk of the water is evaporated, and then the cellulose is transported with pedals and thrown in the air with the pedals in the second section of the dryer, and that's to increase our energy efficiency. The dried material is called fluff, and you can see it in the middle image. It is transported to our pellet press. This is a flat die pellet press, and we produce 6 millimeter of pellets with a diameter of 6 millimeters. And you can see those at the bottom right corner, and those pellets are transported using a conveyor to our deep dryer. And in this deep dryer, you basically have a pellet bed, as indicated with the yellow, and there's a hot air stream, which is apart from the flue gas from the pyrolysis co-combustor, and it is mixed with air to reduce the temperature. And that hot air stream goes through the pellets, drying them to around 90%. And both gas stream from the deep dryer and the fallen curtain dryer go through a wet cyclone before being emitted into the air. So after the pellets are produced, we want to extract some bio-based products out of them, and we're using a pyrolysis technology for this. We have been working together with Net Energy, and Net Energy is a small company that has its own pyrolysis technology, and we're also applying this technology in the pilot. And the picture there is his first pilot installation of Net Energy, and so we've updated that installation for the one in Ada. But what is pyrolysis? So basically, if you have an organic material and you heat it in an atmosphere with a low oxygen content, the material will start to degrade, and a volatile fraction will emit from it. And this volatile fraction can be condensed into a few stages. So one of them, for instance, will lead to a bio oil, and the other will lead, for instance, to the acid, and another will lead to the syngas I discussed it. So the reactor we are using is a flash pyrolysis reactor. There's a short residence time for the gas phase. And yeah, whether you call it the advantage or disadvantage, it yields a higher bio oil yield, in contrary to the bottom product that's a biochar. And due to this high temperature, toxic components in the cellulose are also destroyed basically, and they are removed in the gas phase.
Mark, I have a question.
Oh, yes.
Possible. Dr. King asked, which machine do you use for dewatering?
Basically, it's our own design, and it's a screw press. So you compress the cellulose, and by compressing it, there's less room for the water to be between the fibers, and the water is transported through a sieve.
Another question is this pyro machine also usable for other materials than the homemade pellets?
Yeah, well, they're not homemade, but you could also use them for other organic material. We've also tested them with wood chips, and also we could use it with corn chips or something else. Yes.
So the reaction is nice. Thank you.
Okay, thank you. This is an image of the pyrolysis section. So it consists out of 4 separate units. So you have the reactor. There, the pellets are transported to from our pellet buffer, and we want to make sure there's a stable bed in the reactor. So all the pellets get approximately the same residence time, which is important to keep your product quality stable. And then we're using a flue gas burner of a propane burner, generating a flue gas of around 900 degrees. And we're using this as a thermal heat source for our reactor, because the pyrolysis reaction requires energy. And after the pyrolysis reaction, the volatile component leaves the reactor at the top. That's indicated in the green arrow. And the bottom product, that's a char. It contains a mineral fraction and some fixed carbon. It is removed via a screw at the bottom. So in the separation section, this is where we condense the volatile stream, and it leads to 2 different products: a very viscous bio oil, which is has a high energy density and is sort of a good energy carrier. And we have a pyroligneous acid. It contains most of the water in the insulation, also the organic acids, and it can be utilized on the wastewater treatment plant. And then we have the syngas, which is sent back to the pyrolysis coal burner. Okay, here are these are the images of our pellets and the different components we are creating from them. So we have this chart that leaves the reactor at the bottom, and after activation, it can be used for absorption of micropollutants, for instance, from effluent. We have a bio oil. This is a viscous oil with a high energy density, and most ideally it could be transported out of the location site and used on a different location for combustion, and then to generate steam there. And then by generating steam over there, you're able to reduce, for instance, natural gas consumption. Then we have a pyroligneous acid. Ideally, it would be used on the wastewater treatment plant, since it could enhance the denitrification, and it's useful for the biological phosphorus removal. And then this is also the pyrolysis gas or the syngas, as I described it before. But yeah, you can also see it gives a really nice flame. So this is also suitable for supplying heat for our dryers. Then some challenges, for instance, for the bio oil to get it on the market. Since we're using a waste product, it still has a waste status, and having a waste status for your product makes transportation a bit more complex, and it also gives certain environmental regulations. For instance, the one we're having at our coal burner, that you need a certain temperature, that emissions need to be measured at certain points, but it is also possible to lose to lose that waste status and make it into a product status. Then if you have this product status, you could also get your oil on this list. And for this list, you could get a subsidy. And that's basically a subsidy because you're using a green fuel instead of a fossil fuel. And further, there are some technical issues that obviously can be solved, but due to the usage of cellulose, there's also quite an organic fraction involved, and a part of this organic fraction will, very small part obviously, but it will also come in your oil, and thus it has quite high ash fraction, and this, when combusted, can lead to dust formation on your heat exchanger and reducing heat transfer. And several components could be a bit too high. For instance, chlorine, and then you need special material, special steel. The carbon, so the biofuel, the biochar that we're producing at reactor, you can activate it using several methods. For instance, thermal. Then you'll be using steam or carbon dioxide as a means to activate it. And with activation, you're basically increasing the microstructure of the carbon. So you're increasing the surface area, and this surface area is used as a binding site for different micropollutants. And based on the size of your pores and on the total surface area, you can bind different chemicals. And then there's also chemical means of activation. And with this chemical means, you usually get a bit higher surface area than the thermal one. Yeah, and obviously you can also, like I just discussed, use different feedstocks. And then there's also the composition of your feedstock. So, for instance, with cellulose, you have a high cellulose, and hemicellulose also yield different components of different fractions in your biochar. So this would lead to, for instance, a bit higher bio oil yield and a bit lower char yield. And then also the pyrolysis temperature affects what kind of groups you get, and more of that. But this does make it a bit complicated. And this is also what I'm going to show you in my next slide. So if you want to remove micropollutants from effluent, there are several variables that can affect the absorption or the total removal. So you have this effluent quality, for instance, the amount of cellulose that's in the material, or the amount of minerals, and also whether you have a first flush. It will also affect your feedstock for the next section. And in the pyrolysis section, you can have different temperature and different residence time, which lead to a different surface area. And then after that, you can get different variables for your activation. And then there's also the effluent you want to treat. So the effluent also has different pollution concentrations, and you have a desired removal that you want to keep. So basically, there's a lot of optimization to be done. And then also an obvious interesting question, how circular and environmental positive is this whole thing? From a production perspective, a wastewater treatment plant is very interesting because you have a continuous source of feedstock for your process. And by using this feedstock, you're also reducing the amount of pollution in the wastewater treatment plant. So you're basically reducing your sludge deposition and you're making useful products of that. So this is also nice to use your own products on your own wastewater treatment plant. So you could use your fossil-based active carbon, and you could replace it with your own biochar. And this process can also be most probably made more energy friendly by using different or less energy for drying. This drying is usually one of the largest energy consumers. And what also would be very interested is how does the footprint of our carbon compare to commercial activated carbon? And we're about to make our own bio-based products very soon, hopefully in the next few weeks. So it's going to be very interesting. Yes, thank you for attending this presentation. And I made a short question slide.
Thank you very much, Koos and Mark, for your clarifying presentations. I see that a lot of questions already have been answered in the chat. Please feel free to continue with raising your questions in the chat. And if I look at the program, we start with a final moment to ask if you have any questions left at this moment. You can either raise your hand or use the chat for that. I take a few seconds. And if there are no questions at this moment, we are going to continue with the short virtual tour that we prepared. I see one hand raised by Inka Hobos.
Hello, my name is Inka Hobos, and I have one question. You said that in the ash there are heavy metals still inside. What did you do with the ash?
These are basically the same heavy metals that are also in the sewage water, because it's most of the inorganic fraction is obviously sand, but also has some trace components of heavy metals. But for the char, we're not doing anything with it. It just remains in the char.
So, but the ash you have to dispose.
Yes, but the disposal would be at the moment, after you use the active carbon for adsorption. But the means of this, with which you're able to dispose it, also, is also this metal concentration also determines what means you need to dispose it. So obviously that could be an issue.
Okay, thank you.
I see another question in the chat. How long will this pilot be running?
I'm not that sure on it, but we have a test program for about a month, and I think based on the results from that test session, we'll evaluate how many or what other products we're going to produce with it.
Yes, and to add on that, the total project, so that's more than only the 3 pilots, will run until December 2022, but that's the extended part, and the pilots will be finalized in May 2022. There's also a question I see, have you tested the activated carbon for the absorption of micropollutants?
Yes, prior to this project, we had a sample of cellulose screenings that we dried and paralyzed, and we did some testing on the active carbon to see if it actually worked, and tested it with wastewater and compared it to a commercial active carbon, and I think it absorbed like 60 to 80% or something of the compared active carbon.
And there's also a question, what are the challenges you've encountered with bringing these products to the markets?
Yeah, I think the biggest challenge is the waste status, but if you use the materials on your own location, then you don't have to deal with it, because it's more of a transportation problem. But yeah, that is one of the things that that needs to be solved for the bio-oil, for instance. But for that, it makes it easier when you have the oil available, so you can also do some decent testing on it and make it visible for everybody.
Yes, and small samples can be transported as, of course, always with a waste status to market organizations to do testing. So that's also what we are intended to do. But the pilots just started to be approved as completely safe. So the first batches are being produced at this moment.
I think it's maybe good to say that within this project, we also look at the legal status of resources coming from sewage, and the products from these pilots are also subject to that, of course. There are some differences between countries about these topics, and there are, of course, some barriers that we face, and we see that also with other materials coming from sewage. On the other hand, there are also chances, and they will also apply to the products coming from pyrolysis, I would say. So there's some follow-up from our project in this respect as well, that we will certainly share some more information about on a later stage.
Yes, and maybe good to add on that we just had a legal panel debate last Tuesday, which also has been recorded. So if you want to have this video from us, we can share it with you too. And that was the session all about the legal aspects of those raw materials to bring them to the markets. I think that we have answered all the questions for now. So if that's the case, I think we are going to continue with our virtual tour. And let me explain a little bit. Of course, we would have wanted to invite you to our sewage treatment plant in Ede, where you could have the chance to smell, to see, to feel the products that we have made. And we hope that we can still do that within the coming months. But for now, we plan to make a virtual tour, which we made digitally to show you around the pilots that we have in Ede.
Welcome on the sewage treatment plant of the community of Ede. This plant is part of the Dutch Water Authority Waterschap Veluwe. And on this plant, we go to run innovative pilots from the WOW project together with the partners. Let me introduce our partners, Marit and Mark. Mark is from Pulse Heat, Marit is from CITEC.
I wanted to show you another part, very important for our pilot, because I take you to this direction. because here we have the core screen, and this is important for our pilot. All the wastewater that comes on the sewage plant is first sieved to remove all the bigger parts. So they are removed, then the water goes through the whole plant. So I go inside and see you later? Yeah?
See you later.
Okay, see you later. So now we are in the pilot itself. Here you have the first step, that's the pumping step. A part of the incoming sewage is pumped into the fine sieve installation and the rest is going to the whole treatment plant. This is a fine sieve. We have placed 2 machines. Each machine is good for 300 cubes per hour to deal with. This machine is very simple in its operation. We are waiting for the water to come up into the machine. There is a level control in it, and as soon as the level is high enough, the machine starts to rotate to remove the dry solids out of the water. There is a good, clever PID system, and that regulates the speed of the belt width. So dependent on the amount of water or the how many dry solids are in it, the machine rotates faster. As soon as we have collected the materials on the filter mesh, the filter mesh comes out of the water, the filtrate goes back to the sewage treatment plant, and the dry solids are removed at the back side of the machine. With an air knife, we blow the screenings of the filter mesh, they fall down in a trough, and under the trough we have a pump, and with that pump we simply transport the material to the dewatering machine. Nice that you're here. Maybe
Hello.
you can explain a little bit of the rest of our pilot installation.
Yeah, sure. This is the dewatering machine. So the recovered cellulose still contains a lot of water. And using this machine, the cellulose is compressed. And by compressing it, you're able to remove the bulk of the water. So the separated water is going back to the wastewater treatment plant. And the compressed cake is sent to the buffer over there. The cake is dewatered up to 45 to 50% dry matter. Let's take a look in the buffer. With the cellulose buffer, we're able to dose the amount of dewatered cellulose onto the drying section. Using these 2 screws, the amount of the cellulose is transported to the dryer section. Let's take a look over there. From the other hall, where the material is dewatered, there's this screw conveyor, and it transports the cellulose to this dryer. In this dryer, the cellulose is brought into contact with a hot airstream. This airstream is generated by the combustion of propane. There's a propane burner in this co-combustor. In this co-combustor, there's also something which I'll tell you later. There's also a burner for the synthesis gas coming from the pyrolysis plant. Okay, in this dryer, you have basically 2 sections. There's the flash section. This is where the high temperature flue gas meets the cellulose. And there's an after drying section. So the material is transported slowly and thrown in the air by several screws. The dried material is transported using 2 screws to this pellet press. This is a sample of the fluff. This is the dried cellulose coming from the first dryer, and it is fed to the pellet press. This is a flat die pellet press, and we create pellets from the cellulose to increase the drying efficiency further in the plant and to get some better material handling for the pyrolysis. These are the pellets coming from the pellet press. The pellets that are produced in our pellet press are transported using this conveyor to our deep dryer. In the deep dryer, the pellets are dried using a part of the flue gas stream coming from the co-burner. So in this machine, we have a pellet bed, and there's the flue gas stream going through the pellet bed and leaving at the top of the machine. The pellets that are dried to a dry matter content of approximately 90% leave the machine at the bottom, and they are transported using 2 screws to our pellet buffer. Here in the pellet buffer, the pellets are stored before they are transported to the pyrolysis plant. There's a rotary valve at the bottom of the pellet buffer, and the rotary valve limits the amount of pellets transported to the pyrolysis device. This is the pyrolysis reactor. The pellets enter the reactor at the top, and in the reactor, the pellets are heated using a flue gas stream, and the flue gas stream is coming from this burner. When the organic material in the reactor is heated in an environment with a low oxygen content, the material will decompose. Usually it will combust, but since this is pyrolysis, the material is going to decompose, and it will decompose into a volatile fraction, and the volatile fraction will leave the reactor at the top. The bottom product of the reactor is a carbon-rich char, and the carbon-rich char is removed from the reactor using this screw and stored in this bin. This is a sample of the material we've collected in this bin. It is a biochar, and once activated, it can be utilized at the wastewater treatment plant. There, it can be used to reduce the amount of micropollutants. It can capture it by absorbing, and thereby reducing the accumulation in the surface water, and thus increasing the water quality. The volatile components coming from the reactor are separated into three phases. There's a high energy dense bio oil. There's a pyroligneous acid containing several organic acid fractions, and there's a non-condensable syngas stream. And the non-condensable syngas stream is combusted in our co-burner to generate the heat necessary for the drying. This is a sample of bio oil. The bio oil from this installation has a low water content and a low acid content. This makes it a useful fuel oil. So the bio oil from this installation can be transported to a different location and can be combusted there. The heat from the combustion can be used to generate steam on that location. This is a sample of the pyroligneous acid come from the installation. It contains, obviously, it's a mixture of water with some more volatile components coming from the cellulose. It can be used for the BioP process on the wastewater treatment plant or for the denitrification.
What we are especially enthusiastic about considering this pilot is the fact that we use the bio-based produced products in our own process within our own treatment plant. It was a great collaboration of Water Authority, Vallei Veluwe, Pulseed and CITEC. Of course, we are very proud of this innovation, this innovative pilot. There is a significant future for bio-based products like the bio oil or biochar. Are you part of this future?
I hope this video showed a little bit more about the process behind the pyrolysis and getting out the cellulose from the sewage. Before we continue with the explanation of the decision support tool, I would like to ask a question to my colleague Eric. So Eric, the pilot just was approved to start running. But I was curious, what do you think about the process so far?
Yeah, Katrien, I'm very proud. I'm very proud of this process and this project. And we have realized a pilot plant which provides really good opportunities for research in the valorization resources derived from wastewater. Have I put on the microphone? Okay. In particular, the possibility to extract cellulose from the wastewater will enable to us achieve our goals with regards to circularity. Moreover, it would be fantastic if we be able to remove pharmaceuticals and other environmental harmful substances from the wastewater with a product that we have produced from the same wastewater. Sorry, for my microphone. We have high hopes that we can provide that the concept will prove feasible and successful, cradle to cradle. However, the whole process requires a lot of energy and alignment to make this possible, mainly because water authorities use conventional techniques, but the pilot plant that we was built is fantastic and very innovative.
So that was the biggest challenge from your opinion?
Yeah, I think so. But the whole process consisted a lot of pioneering. And if we had to do it again, it would be better to make a decent action plan beforehand and to really think through. We are interested what goals we are trying to achieve and how to go about it. Moreover, we should have paid more attention to the actual market for these kinds of projects. As there's still a lot of work ahead and bring these projects to the market due to legal restrictions. We are only just on our way, but the possibilities are endless, I think.
Thank you very much, Erik. And I think that's also an invitation for you as participants of this webinar to see it, to help us with finding those market organizations who are willing to test the samples that will come out very soon of the pyrolysis installation. So thank you, Erik. There's a question in the chat. And the question is, currently at which percentage is used the technology for our needs in order to replace our current raw materials? And I think if I translate it a bit, so what is the percentage from this technology? What percentage do we need to replace the current raw materials? So I'm just dropping this question to our fellow partners. Is there anyone who can answer it? Maybe Koos?
Well, it's not so easy to answer the question of to what percentage, because I don't know if we have a complete picture of the market for biochar and that it can replace and bio oils and fatty acids. What we do know is that there is quite a significant amount of screen material to harvest. In the Netherlands, we published often a number between 150,000 tons to 180,000 tons. And in Western Europe, somewhat between 4 and 5 billion tons of material that can be harvested and therefore also can be transferred into other materials. So we know that it can have quite a significant impact. To what percentage is maybe a little bit more difficult answer to give.
Thank you, Koos. Maybe a next question will follow. We will see it soon in the chat, but I think for now your answer already helps. So what we do in WOW, we are going to bring the markets together with the products from sewage we are making in the WOW project. And now, before we are finalize this event, we would like to focus on the decision support tool that has been made from several partners from the WOW project. It's a tool which can be used by sewage treatment plant operators, like the colleagues of Erik, to make them enthusiastic as well to start those circular actions at their treatment plants. And for this, I would like to give the word to Jappe.
Thank you very much, Katrien, for the introduction. And I will share my screen. So indeed, I'm going to tell you a bit more this morning about the decision support tool that we developed within the WOW project. And let's go to the next slide. So what will I be telling you today? So of course, first of all, I will give you an overview of the goal of the decision support tool. Then I will let you know what the decision support tool is about. What are the results of the decision support tool? And also we'll show you what the current decision support tool looks like. We're rounding off the last version at this moment. And then of course, there's some time for questions. So first of all, the decision support tool. We developed this decision support tool as a support and to stimulate water authorities to realize their sustainability goals. And we also would like to use this DST to show policymakers the opportunities for recovery and reuse of carbon-based elements from wastewater. So what is the DST? Well, the DST is an Excel tool which can be used by water authorities that operate sewage treatment plants. And this DST can be used to get a first impression if the influent of a certain sewage treatment plant is suitable for recovery and reuse of carbon-based elements. And there we focus on the products that we develop, or the pilots that we have developed within the WOW project. So we look into, well, the cellulose recovery that was already discussed this morning. The other pilot we look into is the production of bioplastics, microbial bioplastics accumulation, so PHA. And the third product we look into is the production of biofuel from microbial lipids, as Katrien already briefly explained in the beginning of this webinar. And also the idea behind the DST was that we would like to use a limited amount of readily available input parameters. So it's easy to use the decision support tool without having to look up too much information about the influence of sewage treatment plants. And then the outcome of the DST can be used to decide if the technologies are worth a closer look. So if you have a positive outcome, you still need to have a deeper look to see if it's really a feasible option for your sewage treatment plants, but it gives a first indication if it's likely to go through with this decision. So the results of the DST, so what does it show? So when you fill in the composition of an input stream of the sewage treatment plant, we have three options. First of all, the implementation of the technique for cellulose, PHA, and/or lipids is promising. Green. The second one is the implementation of either of the techniques is not feasible based on the input parameters. And the final one is that it's not clear yet if it can be used. So you need a more detailed consideration on one or more parameters to be able to be sure to make this decision. So when you look at the information that the decision support tool gives, so we also provide some extra information besides it's feasible, not feasible, or a further look is needed. We also give an indication about the effects of the WOW technologies on other sewage treatment plant processes. You can, for instance, imagine you already have biogas production, or you have a different...
I'm very sorry, but for some of the viewers, the slides do not proceed. So can you maybe restart the slides sharing?
Yep. Probably it's because I'm highlighted in the screen. Probably because I'm in this, someone put me in the spotlight. I will put myself outside of the spotlight. Hopefully, can you see it now, Katrien?
I can see it.
Okay.
I look at the organization here. Yes, we can see it. Thanks.
Yep. Okay. Do I continue with this current slide, or should I go one or two back?
I think it's good to continue.
Yep.
Yeah,
okay,
we will
perfect.
share the slides anyway afterwards.
Yeah, of course. So besides the outcome of the DST, whether a technique is feasible, we also say something about the effect of the technologies on other sewage treatment plant processes. As I already explained, for instance, if you have biogas production installed, so does one of the techniques affect this processes, because that's something you would not like to occur. It gives information about technical aspects based on the information from the pilot. So how much space do you need and stuff like that. I will show you a bit later on. Economic aspects based on a techno-economic assessment that we are performing within the WOW project. And it also gives information on environmental and sustainability aspects. And finally, it gives some information about social aspects. So what does it look like? This is when you start up the decision support tool, the first tab that you will get in the Excel file, and this is basically a brief explanation of what the decision support tool does. And when you would scroll down, this is a screenshot, so I can't scroll down at the moment, then it would give you more information on how you can use the decision support tool and what you need to fill in. So then a next step, that's of course the information that you need to put in the decision support tool. So the decision support tool you can fill in up to 50 different influence of sewage treatment plants, and you can fill in the name and the location of the sewage treatment plants. Easy to see later about which sewage treatment plant the result is. You need to fill in whether the sewage treatment plant has a primary treatment, yes or no, because that's important for PHA production. The next parameter you need to put in is the percentage of sewage from households, and we have 3 options there available, which you can click on. The amount of population equivalence, PE, inwoner equivalent in Dutch. So that's information you need to fill in. And finally, you need to fill in information about the COD and or BOD. And if you don't have this information available, we use a standard value as shown here in red. And you can also change that standard value if you have that information from your sewage treatment plants. So this basically is all the information that you need to fill in. And then we will go to the results. So first of all, you have a tab with the overall results of the DST. So this gives an example with some fake numbers that we used in this case. So here you see the names of the sewage treatment plants and the location. And here you see per product or per technique, whether it's feasible, so in green, whether it's not feasible, orange, and in gray, you need to take a further look. And the pie charts over here give an overview which percentage of the sewage treatment plants that you put in give either of these results. If you would like to take a more specific look, and this is the one for PHA, you can, for each of the different techniques, you have a separate tab where you can find per parameter that you filled in the outcome. So why, if it's green, so then of course it's positive, but you can check why a certain sewage treatment plant does not give a positive outcome. And of course, it also gives the overall results. And as I already told you, we also have a fact sheet tab where it gives you different information. So that's also one for each of the different techniques. This one gives an overview of the techniques and the effects. So different techniques that can be implemented already at a sewage treatment plant. And here you have information. So the pink one says there is no impact on the process. The yellow one, it possibly has an effect, and the brown one, it definitely has an effect on the process. And in this case, it's the fact sheet for cellulose to produce char, acetic acid, and oil. And as you can see, there's also a red triangle. And if you go to that red triangle in the Excel, then you get more information as to why there is the effect. And then finally, there's also in the fact sheet information, as I told you, about the technical aspects, economic aspects, environmental and sustainability aspects, and the social aspects, in this case of pyrolysis as an example. And as for instance, with the technical aspects, you can say something about the dimensions, the status of the technique, or electricity use. With economic, we look at CAPEX and OPEX as an example. With environmental, it says something about odor or noise or visual pollution. And with social aspects, it says something about health and safety, public acceptability, and also legal aspects. Well, as you can see, something is still put there in red because we're still in the latest stage of developing this based on the results of the pilot. So that concludes my first overview of the DST, and the idea is that the DST is publicly available after the summer holiday. So then it will be put on our WOW website and it will be available for everyone to use. So thank you very much.
Thank you very much, Jappe, for your explanation about the decision support tool. Are there any questions for Jappe, or maybe you have some questions left for the previous presenters? Please take the floor by raising your hand or by asking it in the chat. I will just wait a few seconds. No questions so far?
Well, means I was hopefully very clear about what the DST means.
At least for me, you were very
Yeah.
clear. So, okay, then I think we are going to finalize this event. We have a slide for that. So maybe it's good to share this final slide. So the website of the WOW project was already shared in the chat, so you can have a look at that and also look at our other activities that we have next to these cellulose pilots and the decision support tool. And as I previously mentioned, we have 2 other webinars to come, one the 7th of June about the PHIA pilots, and one the 10th of June, which is next Thursday, and will be about the lipids pilots. And last Tuesday, we had a webinar about the legal aspects, which I previously mentioned, and which you can also see again on YouTube, and it will be shared on our website as well. So if there are no questions anymore, I would like to thank the presenters to share your latest information about the pilot and to show our virtually through the cellulose pilot. It was really nice to see it after home working for so long. And then I would like to thank everyone, every guest here, and also the people who will view it on YouTube to see all about our project and the pilots. Many thanks, and hope we will meet each other the coming months, or maybe at our final event, which will take place physically and digitally early next year. Many thanks.